Hello, you're welcome back. All right, so we are going to be looking at temperature and thermometers in this video. All right, so let's start by definition. What's temperature? Okay, and why is temperature different from heat? Because students do actually confuse temperature, all right, with heat. All right, so now temperature is commonly defined as the degree. Okay, temperature is commonly defined as the degree of hotness, degree of hotness, and of course coldness of a body. Now I will simply say that this definition, though, is correct to some extent, okay, but it have some constraints, because sometimes if you want to actually talk about the degree of hotness and coldness of a body, okay, sometimes there are some conditions that will make your measurement to be wrong, especially when you are using feeling. Okay, imagine where you have an object. You want to know how hot this object is, then you now touch it. If it is hot, okay, if it actually feels hot on your palm, you say, okay, the object is hot, it's very hot. Okay, if it is cold, you say the object is cold. Now you discover that that particular method of measurement is subject to emotional state, because your body temperature can actually affect the reading of your feeling, okay, on this particular object, right? So though this definition is really valid to some extent, but I will define temperature in another way. Okay, I will simply define temperature as a physical quantity. Okay, as a physical quantity. Okay, quantity which actually measures, a physical quantity which actually measures, it measures rate and of course direction of flow, of heat energy, direction of the flow of heat energy. So we simply mean that temperature is not an energy, it's not heat. Okay, heat is actually present in a body. Okay, a body have a particular heat content, but for us to know which body has the heat, okay, the direction to which this heat is actually flowing, then we use temperature. Temperature is a physical quantity, okay, that can actually measure that. Now let me illustrate what I actually mean. Okay, how do I know the direction of flow of heat if possibly I have a hot object and a cold object? Okay, this is a hot object and a cold object. Okay, so now if you bring a hot object and a cold object, discover that heat will always flow from a hot object to a cold object. So I can know the direction of the heat if and only if the temperature of the hot object is actually increasing. If the temperature of the of the cold object, please pardon me, is increasing, then I now measure the temperature of the cold object. I discover that the temperature of the cold object is decreasing. Okay, and of course I will measure that with a thermometer. Then I can simply say that, okay, this is the heat is actually flowing from this particular object to this object. That's the direction of the flow of heat. All right, so do you understand? I can also measure the rate at which the heat flow by measuring the time for me to get a particular rise in temperature. So the rate of flow of that heat can also be measured by the temperature. So I measure the temperature at some time interval. I'll be able to get the rate of the rate of flow of the heat energy. All right, that is just by the way. Okay. Now, as I said, measuring the temperature of a body by just feeling it is not ideal. So how do we actually measure the temperature of a body? Okay, we measure the temperature of a body by the instrument, okay, called thermometer. Now the question is, how is thermometer constructed that makes it accurate tool for measurement of heat or temperature? All right. Now, thermometer does not have anything to do with feeling. Okay. Rather, thermometer actually employs the help of some substance. Okay, substance known as thermometric substance. So, thermometer is actually constructed with by the help of substance called thermometric substance. Why are they called thermometric substance? Why? Because their temperature, their physical properties, okay, some of their physical properties, some of, okay, or a particular physical property of that particular substance, physical property, what happened? Changes with the change in temperature. So there's something about that substance that actually changes, okay? That's the property, physical property of that substance that changes with the change in temperature. So anytime temperature change, that property changes. So we can actually utilize that change of that property, okay? Utilize the change, please pardon me. Okay, let me just abbreviate that. Temperature. Okay, utilize the change of that particular property to construct a thermometer so that if I now want to actually measure the temperature of a body, then I discover that I've just placed the thermometer of on that body, then that physical property in which that thermometer is actually being constructed, okay, the physical property of the thermometric substance in which that thermometer is being constructed will change based on the temperature of the body that I'm actually measuring. So let's look at this thermometric substance, okay. This thermometric substance, let's start. One of it is a thermometric liquid, okay, they are in their liquid form. Okay, please pardon me. All right, so that's alcohol and mercury. Now the question is, what is the properties of alcohol and mercury that actually changes with temperature that can employ in construction of thermometer? That property is what is known as linear expansivity. Okay, linear expansivity. Or linear expansion, okay. Okay, please pardon me. Or generally, I can call it thermal expansion. What does it simply mean? Anytime the temperature of, okay, alcohol actually increases, then alcohol will actually increase in length, and the same with mercury. So that way I can actually use it to construct what is known as mercury in a glass thermometer, okay, having a particular a narrow capillary, okay, having mercury inside of it. So it has mercury inside of it. So if I carry this thermometer and place on an object, okay, then what happened? The mercury inside the capillary will rise based on the temperature of that object, okay. The same thing happens with alcohol. So linear expansion, or generally you can say thermal expansion. All right, then number two, please pardon me. All right, number two, another property or another substance we actually uses is known as platinum. Platinum is a metal, okay. So what is the properties of the platinum that actually changes with temperature? The property is actually the resistance. So the resistance of platinum, okay, actually changes with the change in temperature. So I can actually use that to construct a thermometer. Number three, gas molecules. So what is the properties of gas molecule? Okay, we've actually talked about this when we treated, remember, gas laws, which we know that from pressure law, okay? temperature is actually proportional to temperature is proportional to pressure. Okay, so the thermometric properties of gas molecules that actually changes, okay, is simply the pressure. The pressure is a property, pressure of gas molecule, which of course is proportional to the temperature. So, and of course at constant volume. Remember, that means we use a Boyle's law to actually construct gas thermometer, okay, at constant constant volume. So that way, if actually if I if I use gas thermometer, okay, as the temperature of that gas increases, I can measure the pressure. I can use the pressure, okay, that I measure to know the temperature at that particular, okay, the temperature of that body. Please pardon me. All right. Then number 4. All right. What are we looking at again? We'll look at an instrument known as a thermocouple. Okay. A thermocouple, as the name implies, is made up of two metal that is actually joined together. All right. So, what is the thermometric properties of thermocouple? Is the change in EMF. Change in EMF of a thermocouple, which is actually proportional, which changes with temperature. So, a thermocouple, okay, a thermocouple, the EMF that is produced by a thermocouple changes with change in temperature. All right. So, if there are other, I will actually bring them up. Okay. So, let's now go to how, okay, these thermometers are actually constructed, how they are calibrated. Remember, it's one thing for you to actually get to know the properties of the thermometric substance, but how do you actually calibrate it? How do you actually, okay, use that properties? Okay, how do you relate that properties with a particular temperature? So that's actually lead us to what is known as temperature scale. So that means a particular thermometer should actually use a particular scale. All right. So basically, the scales that we actually use to calibrate our thermometer, okay, temperature scale. Okay, we'll have the centigrade or the degree Celsius scale. All right, degree Celsius, Celsius scale. We can also use Fahrenheit. Okay, but for the thermometer that is used, the clinical thermometer, basically, okay, use Celsius scale. In fact, Celsius scale is much common, right? So Fahrenheit scale, that means that thermometer is calibrated based on Fahrenheit. Okay, then we can use Kelvin. Kelvin is for the absolute temperature. In fact, Kelvin is actually the SI unit of temperature. So you can create a scale based on Kelvin. All right, so now for us to actually use, we can use any of this scale, but the very first thing you need to know is actually to get your fixed point. Fixed point. What are your fixed points? The fixed point is talking about the lowest and the maximum temperature that thermometer can measure. So fixed point. There are two fixed points. Okay. One is the lowest temperature, which of course is known as the lower fixed point. Lower fixed point. Lower fixed point. Of course, the lower fixed point based on a Celsius scale, okay, is just the temperature of melting ice. The temperature at which ice actually melts, melting ice. All right, and we know that temperature of melting ice, okay, is simply 0 degrees Celsius. Then the other fixed point is what we call the upper fixed point, maximum temperature, okay, upper fixed point. All right. So of course, this is temperature at which water, right, is actually being converted to steam. So it's just the temperature of steam. So water is converted to steam at a temperature of 100 degrees Celsius. So I can actually draw, okay, a scale based on Celsius just using a line. It is easy. Okay, to then a line here, I have the lower fixed point. So for Celsius or centigrade, so I have the lower fixed point of Celsius, which is 0 degrees Celsius. I have the upper fixed point, 100 degrees Celsius. What is different with Fahrenheit is different with Fahrenheit. For Fahrenheit, okay, the lower fixed point, which of course is equivalent to the temperature of melting ice, is 32 degrees Fahrenheit. And the upper fixed point is 100 degree Fahrenheit. But, oh, please, not 100 degree, 212 degree Fahrenheit. 212 degree Fahrenheit. Now, one good thing about temperature scale is that temperature scale can be converted. You can convert from one scale to another, okay? Or you can convert from one thermometric properties, okay? You can convert a temperature scale of Celsius, okay, to the thermometric property, let's say length or even resistance. So they are all interconvertible. Whatever you use to construct, whether it is you're using volume, it can always be converted. Why? Because you can convert it, because in as much as you have you've drawn your upper fixed point and lower fixed point of, okay, of the Celsius, which we know is 0, okay, by standard 0 degrees Celsius and 100 degrees Celsius, you can convert it to anything. Okay, for example, okay, I'm looking at temperature conversion. So I'm using this now to illustrate how to convert temperature conversion. So what I'm going to give you now is something that you see in book as a formula, but sometimes our students don't know how that formula is being generated. It's just very important for you to know the source of a formula, so that no matter how the question comes, you'll be able to handle it. Okay, for example, now let's say I want to get a temperature in degrees Celsius. Okay, let me call it theta degrees Celsius. Okay, that is actually equivalent to 40 degrees Fahrenheit. All right, I don't need to cram any formula. All I just need to do is just to take this scale, the difference. Okay, I take the difference between the upper fixed point and the lower fixed point. Okay, then of course divide it by the difference between that temperature and the lower fixed point. So in this case now, comparing this temperature of Celsius and that of Fahrenheit, it is just very easy. All I just do, I will start with the distance between the lower fixed point and upper fixed point. You know, of course, it's going to be 100 minus 0 divided by the distance between the temperature I'm looking for from the lower fixed point is just going to be theta minus 0. Is equal to, the same thing happens here, the distance between upper and lower, 212 minus 32. Okay, then divided by the distance between, okay, that temperature, 40, then of course minus 30, minus 32, please pardon me. All right, so I think from what I have here, I'll simply, this 100 minus 0 is 100. Theta minus 0 is theta. 212 minus 32, that's 180. Then of course 40 minus 32, that gives me 8. So if I cross multiply, okay, I make theta the subject, theta degrees Celsius. All right, so my theta degrees Celsius temperature in Celsius, that's equivalent to 40 degrees Fahrenheit, is going to be equal to cross multiplying. That's going to be 100 times 8, then divided by 180. As simple as that. As simple. In fact, everything that have to do with temperature conversion is just this principle. If you know how to apply this principle, no matter what you're converting, whether you're converting from Celsius to resistance in ohms, you're converting from Celsius to probably volumes in cm cube, it is still going to be this. Just use this, okay, to do that. You can get your answer. So at this point, just use your calculator and work on this and get your temperature. All right, so that is temperature conversion. So we are going to look at more questions in the next video. All right, see you in the next video. Thank you very much.